Hello there, folks. Today's lesson is coming to you from 1.2, and it is properties of real numbers. And what we have up here that you need to write down is a Venn diagram. And basically we're going to talk about the different types of numbers, and there's different categories or sets of numbers. And so I want to kind of go through all of them with you. First, in the innermost part of the diagram, we have what we call the natural numbers. And you'll notice that next to the word natural, we have in parentheses a capital letter N. This is the letter that we use to abbreviate the natural numbers. So anytime, for example, in your homework, you're going to have to classify different numbers. Instead of writing out the full word natural, you can abbreviate that with the capital N. And so what are natural numbers? Natural numbers are oftentimes referred to as counting numbers. And I will remind you that when you're counting something, like for example the fingers on your hand, we don't start counting with 0 and we don't start counting with negatives. We don't say that you have -1, 0, 1, 2, 3 fingers. We don't even say you have 0, 1, 2, 3, 4 fingers. We start counting with the number 1, 2, 3, 4, 5. So natural numbers basically don't include any of the negatives, don't include 0, so it starts with 1. And it could be something like 2, 17, 95, positive integers basically. So that's the natural numbers. The next category is the whole, and I think that you understand how a Venn diagram works, and so it means that while the natural set is inside of the whole box, it means that automatically natural numbers are also classified as whole numbers. And for whole numbers, we abbreviate that with a capital W, and the whole numbers are pretty much the exact same thing as the natural numbers. The only thing that gets added to the whole numbers is the number 0. So 0 is the only number that gets added to that set. Otherwise, it's pretty much the same thing as the natural numbers. And then we have our next set, which is the integers. And I know that you want to think to yourself, you want to abbreviate that with an I, but actually we have another set later on, the irrationals, which are going to use the letter I. So for integers, we're going to abbreviate that with a capital Z. Don't ask me why they picked Z, but that's the letter that we're using. And for integers, you're now adding all the negatives. So we already had natural, which included all of the positive integers. We added 0 to get the whole numbers. And now we're going to add to the set all the negative integers. So things like -3, -2, 0, 5, 103. Those are all examples of integers. And that's pretty much the world that most of us like to stay in. Most people don't like fractions and that kind of thing, but obviously fractions do exist, so we do have a category for them as well. And for fractions and stuff, we have the next set, which is the rational numbers. And again, you think rational R, but we already have R for real, so we're going to use the letter Q to represent rational numbers. And rational numbers, I'm going to go ahead and with the rational numbers, I'm going to give you a little bit of information about rational that's going to be off to the side over here. In addition to the Venn diagram, rational, a couple of things. A fraction, any fraction is automatically rational. Automatically rational. So oftentimes on questions we'll ask you if something is rational or irrational. When you see a fraction like 1/3, -7/8, any fraction is automatically rational. All right? So that's one thing I want to say. The part that gets confusing for most people is when they're dealing with decimals. Okay? Well, again, when you see a fraction, automatically it's going to be rational, but sometimes you're looking at a number that's decimal, and so it's important for us to make a distinction here. Rational numbers can appear to be decimals. As you can see here, we have 0.125, but there are two conditions. The first condition is that the decimal has to terminate. If you have a decimal that terminates, then it is automatically rational. So as you can see, we have an example there of 0.125. That decimal terminates, it stops, it ends, and therefore it is considered rational. The third point that I want to make is that you can also have a decimal that is non-terminating. In other words, it goes on forever. But if that happens, the only way for a non-terminating decimal to be considered rational is for it to be a pattern, so non-repeating. Sorry, I wanted to have a pattern, not have a pattern. So let's do that again. And it needs to be repeating or have a pattern. So for instance, I'm going to put here pattern. So for example, you've seen them before. For example, as a matter of fact, 1/3, if you actually put 1/3 in the calculator, you're going to end up with a decimal. It's going to be 0.333333. And since the 3 is repeating, that's what we mean by it having a pattern. Okay, so it could also be something like 0.67676767. It could be 5.394, and you guys know how that works. You would write a number like 5.394, and then that whole part that repeats, you put a bar over it. So anything that has a decimal with a bar over it, which indicates that it's repeating, is going to be considered rational. So just again, any fraction, automatically rational. Any decimal that terminates, rational. Any decimal that doesn't terminate but repeats or has a pattern is rational. Which brings us then to the irrational. The irrational numbers and the rational numbers have no overlap. You can see from the diagram that all of these boxes are one inside of the other, except for these two boxes, this big rational box here, and then we have our irrational. So the irrational and the rational have nothing in common. They are mutually exclusive. You cannot be irrational and at the same time be rational. So don't ever do that. And again, for the irrational, we're using the capital letter I to represent the irrational numbers. And some of the irrational numbers that you might be familiar with is like something like pi. You might know about pi. That's 3.14159, blah, 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 da, da, da. And it goes on forever and it never repeats itself. So for irrational, we're going to do the same thing we did over there. For irrational, you have basically non-terminating and non-repeating. So again, I want to be clear that both rational and irrational have decimals that are non-terminating. But in the case of rational, the non-terminating decimals are repeating. And in the case of irrational, the non-terminating decimals are non-repeating. There's no pattern here. Okay? Another number that you might not be aware of is another, we know that we abbreviate pi as 3.14. There's another one, it's E, the natural number E, we use it later on in Algebra 2 and Pre-Cal and AP Cal, is approximately 2.718. But again, that's another irrational number. And then you have things like square root of 2, square root of 7. And if you don't know whether or not it is or isn't, a really easy way of checking is to put it into the calculator and look at the decimal. Get the decimal approximation or whatever, and look to see if there's a pattern or not. If there's a pattern, then it's going to be rational. If it's not having a pattern, then it's going to be in the irrational category. But anyway, so that's irrational. So then our very last category, as you can see, it's kind of the big mother of them all, is that we have real numbers. And for the real numbers, we use the capital letter R to be real. And that's kind of the end of the whole thing. And you'll notice that the real, which is the black box, if you can see the colors, is kind of encompassing everything. So we said earlier that there's no overlap between rational and irrational, but both of those types of numbers are considered to be real. So everything on this board is real. And later on in the year, we'll be talking about what's non-real or imaginary. But for now, that is your number sets. So we're going to do some examples here. The first thing that we're going to be asked to do is to name the sets of numbers to which each number belongs. And I want to emphasize here the word sets. It doesn't say sets, so it's not singular. You should have, in most cases, more than one option for each thing. And we're going to use our letters that we, our abbreviations, okay? So the first set we have, the first example, number that we have is negative 23. Negative 23 is not natural because it's negative, and we talked about that. We start with positive integers, so it's not natural. It's not in the whole numbers because the whole numbers are the same thing as natural with the addition of 0, and that's not 0. So the first set that the negative 23 can be a part of is the integers. And for the integers, we have the letter Z, remember? So we're going to put Z. But because it's an integer and the integers are inside of the rational, then this number is also rational, which is the letter Q. And then because it's a real number, we're going to put R as well. So all of these are real numbers, so they're all going to have R. So if we want, we can just go ahead and put R on everything, because it's automatically going to be real. There's nothing in here that's imaginary, at least not yet. So we've got integers, rationals, and reals. And now what about the square root of 50? The square root of 50 is obviously not an integer at all. And if you actually go to your calculator, as I was saying earlier, let's say you're not sure what square root of 50 is. The square root of 50 is 7.071067812, and on it goes. So we now know that we have a non-terminating decimal. So it's not an integer, so it's not whole, and it's not natural. But the question is it rational or is it irrational? Well, it has a non-terminating decimal, but does it have a pattern or does it not have a pattern? And I'm looking at this again, and again, if you have it on your own calculator, 071067812 does not appear to have a pattern. So because it has no pattern and it has a non-terminating decimal, we're going to say this is irrational. And for the irrational numbers, we're going to be using the letter I. So it's irrational and it's real. All right. So that's going to be for part B. And then lastly, we have C. Again, it's not a natural number. It's not an integer. It's not whole. But it is a fraction. And we said already that anything that's a fraction is automatically rational. And rational is going to be Q, I believe. And then, of course, it's real. So we've got rationals and reals. So all of them had at least at least 2 answers. So make sure that you don't just give me one answer for each one. It can be part of more than one category. All right, so now you have 4 examples to try on your own here. And once you've done that, you can move on to the next example, or sorry, the next set of properties that we have. And a lot of these you should be already familiar with, but here they are for you to write in your notebook in case you forget them and you might need to glance at them on a quiz or a test. But we have the commutative property. And what I will tell you about the commutative property is it's all about order. When you think about commutative, you want to think about order. It doesn't matter which order you add and subtract in, or what order you multiply in. So here we go, A plus B, same thing as B plus A times B, same thing as B times A. Then you have the associative property, and the associative property is all about grouping. So you're talking about having 3 things or more, and so you can see we're adding 3 separate numbers. But your brain can't actually add all 3 at the same time, even though it does it very fast. What your brain automatically does is it collects 2 at a time, and it starts adding. So it's all it's saying here that if you collect the A and the B first and then add C, it's the same thing as collecting B and C first and then adding A. And same is true for multiplication. The grouping of doesn't really matter in your final result. And then we have the identity. The identity for addition is 0. Which basically says that 0 added to anything is not going to change it, it's going to stay A. And then you have the identity for multiplication and division, which is 1, which basically means that if you multiply anything by 1 or divide anything by 1, you get itself back, A back. And then we have inverse. And it's important to remember that inverses always produce identities. When you have 2 inverses together, like A and negative A, and you add them together, you will get 0, which is the identity. So 2 inverses will always produce the identity. And even over here we have A times 1 over A. So the inverse of multiplication is division. So again, 2 inverses are always going to produce the identity, which is 1 for multiplication and division. Closure. Closure is an interesting one. Closure just means that since we're talking about real numbers, if A and B are both real numbers, when you add 2 real numbers together, you'll get another real number. So when you add 2 real numbers together, it's impossible to get an imaginary number. And that's basically what closure means. When you multiply two real numbers, then you will get a real number back. And then we have our distributive property, which I'm sure you're pretty much aware of. And here we have that for you. So we want to write these down, make sure they're in your notes. And then we're going to do an example here. And this says, name the property that's illustrated by 5 times 4 times 13. So what you can see is that here we have the parentheses around the 4 times the 13. And here we have it around the 5 times the 4. So what property deals with grouping is the question you should be asking yourself right now. And we said before that that's the associative property. So you have that in your notes from earlier, is that it doesn't matter which ones you group. So if I multiply the 4 and the 13 first and then times by 5, it'll be the same thing as 5 times 4 first and then times 13. So we're going to put up here that it's the associative. Let's see here. Trying to get a different color up here. The associative property of multiplication. Now, had we been adding, we would say associative property of addition. But right now we're multiplying, so the associative property of multiplication. And so then there's another example for number 2, and you can do that one, and then we'll move on to our next example. Find the additive inverse and the multiplicative inverse for the number negative 5/8. The additive inverse is the opposite of negative 5/8, which would be positive 5/8 for the first part of example 3. We're doing the opposite. So basically, what can you add to negative 5/8 is going to equal 0? Well, that would be positive 5/8. And then the multiplicative inverse is the reciprocal of this guy. So the inverse would be negative 8/5. And again, that's because if I multiply negative 8/5 times negative 5/8, I will get positive 1, which again is the multiplicative identity. 2 inverses will always produce the identity. So these are our 2 answers for example 3. And then you have a couple of examples or a couple of problems to do there for the do-it-yourself number 3. And then we have our last example of today's lesson. And it is to simplify, using the distributive property, we're going to simplify this little guy. So, the distributive property says that we can take and go 3 times 2q plus 3 times r. So literally 3 times 2q and then a plus 3 times r. And the same thing for the other side. We're going to do 5 times 4q. And then this is a negative here, or you can just go plus 5 times negative 7r, which is 5 times negative 7r. Okay, so now we're going to simplify that. 3 times 2q is 6q, 3 times r is 3r, 5 times 4q is 20q, and then 5 times negative 7 is negative 35r. And then our last step is to try to combine like terms. So we can see that we've got 6 q's and 20 q's. That's going to be 26 q's. And then we have 3 r's and negative 35 r's. And that's going to be negative 32 r. And so this would be our final answer for the example 4 here. So now that leaves you with do-it-yourself number 4. And once you have done the do-it-yourself number 4, you will have completed your notes for this lesson. And I will see you in class next period. Thanks for watching.